Ja. Virker denne? Nei. Virker den nå? Ok, fint. Velkommen til denne oktoberutgaven av GeoWednesday. Nasmul will talk in English, but I'll talk in Norwegian. So you have to bear over with that. Det en glede for meg å ønske dere velkommen til GeoWednesday nå i oktober. Mitt navn Jens Jaren. Jeg her fordi at det ingen andre fra øvrigheten som var til stede i dag. Så da skal jeg introdusere Nasmul. Nasmul, han har sin bakgrunn fra Bangladesh og har bachelor og master fra Dhaka-universitetet en gang i urtiden, og etter det så var han ansatt i et geofysisk selskap, og også i den bangladeshiske geologiske undersøkelsen i flere år. Etter det så fant han ut at han trengte litt påfyll og reiste til Trondheim av en eller annen merkelig årsak, men han hadde funnet på nettet at det var et veldig fint sted å dra til. Så da tok han en mastergrad til der innenfor geofysikk, før han kom til oss for 20 år siden, mer eller mindre nøyaktig 20 år siden, og tok en doktorgrad for Knut Bjørlykke, som sitter i salen i dag. Det var innenfor det som i dag kalles rock physics, eller bergartsfysikk, hvor man kombinerer geofysikk og geologi for å få et best mulig oversikt over hva slags type bergarter som finnes i undergrunnen. Det arbeidet han gjorde da var helt banebrytende, og Nasmul å regne som en av verdens fremste innenfor mekanisk kompaksjon av finkornede sedimenter. Det har han bygget videre på, og i dag så skal han snakke om no seal, no deal, og seil i geologisk sammenheng. Det altså kappebergarter, bergarter som ligger over reservoarer, og det viktig at disse tette, og for å vite om disse tette, så trenger man å vite egenskapene til dem ut fra geologiske og geofysiske data, og det det som Nasmul hele tiden har vært interessert i, å kombinere geologi og geofysikk, og få mer ut av dataene enn det en vanlig geolog og en vanlig geofysiker sier. Du må vente med spørsmålene til... Nei, han ikke forseglet. Nasmul will give this talk in English, and you will hopefully not hear much more from me before or after his talk, but all questions are welcome. So, Nasmul, the floor is yours.
Yeah. Yeah, thanks, Jens, for a generous introduction. And then, hello, everybody. Welcome to this session. It's a pleasure to be here to give a talk. One thing I noticed when I came here, from audience, they ask for, okay, it should be general. You should show many movies and photos, not too much text, and obviously no equation and other things. But in science, it's not that simple, but I promise I'll try to follow like that, make things more general. So only 2 equations will come and go in a few seconds. So you don't need to focus on that. And the video, I don't have that many, but I have one. But mostly photos you'll see. Yeah, Jens already introduced this title, like no seal, no deal. And if it is CCS or large-scale CCS, obviously seal or cap rock, where you, beneath seal or cap rock, you store CO2. So if anything happens on seal, everything will be kind of disaster in that sense. So seal obviously very, very important component in this CCS kind of work. So it will be mostly focused, that's why, on that direction. Before I move further, I just would like to give a bit short explanation about this schematic diagram I took from Northern Lights JV. So you see, that could be the future in Norwegian CCS. Like in here, you see lots of industry or any other kind of emitters where CO2 would be captured. And then captured CO2 will liquefied and transport through ship to one of terminal close to the shore. And from there, with a pipeline, like you see, it could be a few 100 meter or 50, 60 meter from the coast. Then we'll basically permanently inject CO2 underground geological formation. So this is the exact schematic from Northern Lights or Longship project. I guess everybody knew about. So it could come a bit more later. Yeah, before I go, it's a busy slide, but I should really acknowledge, because this presentation or results you will see came from those people worked together for 2 CCS projects ended just before summer this year. So 2 PhD, Jürgen and Jamil, they were important part in this CCS research. And then 1 postdoc, Manjar Fawad, he was also very, very centered in this research. And then colleagues like Jens and Knut, obviously, always with us. And some colleagues from NGI as well, like Lars Granda and other. So we work as a team, and sometimes also like outside of Norway as well. So the 2 projects I work, many research institutions were there, as well as many industry also supported both of them. So I'll come back later. But before go too in depth, just I splitted my presentation in 4 sections. First, I really like to give you background of this talk, or background related to CCS, why it is important, why people are talking about this. And then objective sets for this presentation. Obviously, I'll introduce the study area. Initially, you see the title is Offshore Norway, but here, most specifically, I'll show these potential storage sites surrounding the big or giant trawl field. And then database and methods, obviously more scientific. So here we have more kind of integration like geology, geophysics, rock physics, petrophysics, petrography, and machine learning. And then data we use, mostly well log and seismic, because those seal or cap rock, not that kind of focus when those wells drill. Those are cap rock, so most of the well company mostly core from reservoir, not for seal. So seismic and well log is kind of key component in this phase when we are targeting for future CO2 storage, like large scale, where it will be, site selection, all those issues. So seismic and well log, drilled earlier. And then, I'll show a few results, like first based on well log analysis, and then in field scale, how we propagate those results for better understanding of the area for site selection and conclusion. Yeah. So in background, this is kind of historical record. You see data from here, like years, started in 1800 until somewhere here present, and then global CO2 emission. That's like billion tons. So you can see the trend. Natural process, more or less nothing. Then industrial is you have some increment of CO2, but really triggered when this petroleum age came, and then lots of CO2 emission related to all those fossil fuels like oil, gas, and coal as well. Then basically, like our responsibility to capture those CO2 and store where it was, that could be a nice kind of balance. So that I'll tell later. So if nothing we do, then that would be the trend for the future. But it was a lot of discussion, and Paris Accord and then IPCC report, we have to do a lot about that, and we should do as quick as possible. So this is now the present trend, but it will not fulfill this net zero. We need another 50% reduction. And that could be only possible if we are managed to do large-scale CCS storage, not like small here and there, really, really big. So I'll give you a bit hints on that as well. So this is CO2 concentration in atmosphere. If you see 1800, somewhere around 280 ppm, but now we see it's really double. So that means not only like we capture CO2 from all those industrial sources and we are burning fossil fuel and capture from them, but also air capture CO2 from air, already in the air. That could be kind of focus as well, if we really target for net zero to prevent global warming. Yeah, before move further, it is always better to see in terms of continent, like how this thing works. So those are the size. You can see large and red one, that's the Asia, contributing CO2 emission annually more than 53%. So if I click here, then you can see the number. Asia, 19 billion ton. That means total CO2 emission, more than half Asia is emitting. And then North America, Europe, more or less same, very close, 6.5 and 6.1. Then Africa, South America, Oceania, not that much, because all the CO2 related to development, energy consumption, habit, lifestyle. And then this is another focus, like aviation and shipping, really contribute some sort of volume, like 1.15 billion tons per year all over the world. So there are some initiatives to capture CO2, like shipping industry and aviation, or reduce how we can do that. That's important. So if you see a bit global scenario, like how it works, so you can easily see with brightness where you have most CO2, like US, Europe, India, China. So this is a real scenario, like right now, what do we have? So let's see a bit more about which country emitting most CO2. And in that perspective, I would like to go a bit back, like started from 1950. You see mostly Europe and United States, they were emitting the most, and then it was around 2.5 billion tons. So billion tons, that's the important thing. And if you see China over there, so it's really down there, and it's around 78, 79 billion tons, million tons, not even billion. And then Norway, obviously, very small. I put also Bangladesh here. It's nothing. That really reflects like how much energy you use. So if I show you time steps like every 25 years, you see the dynamics. So China from somewhere around there now moved over there. And Europe, even more emission, United States somewhere over there. And then another 20 years, if you see around 2020, still Europe and United States, they are dominating, but China really catching up. And if you see Norway, from just a small amount, now it's 42 billion. So it's not that small anymore, a million. And then this is the latest, like if you see now the situation of China, so where they are, more than double of US and United States. And then Norway reduced from earlier one, you see. So some initiatives are going on in Norway. That I'll show you later too. So Bangladesh now over here, it was below or lower than Norway, now higher. So that reflects like when you are in developing country and moving towards real development, you need all those energies. And when it is already developed, you can think a lot about luxury, all those things. Yeah. So this is another nice slides. Like, then question. China is emitting a lot, India is coming, Europe emit earlier, now it's less, so who will pay? Who will contribute most? That could be the scenario. So see this cumulative CO2 emission from like historic record until recently. So Europe emitted 500 billion tons. And then United States also like that. But China so far emitted half of Europe or US. So that's and if you think India is not there, just cross 100 billion tons. So that means, there are political discussion like how, who can take over, who should start first, and when we have this understanding, like all those developing countries, they don't have maybe technology ready, but developed country may have technology, so they can share the technology to make a good balance, and we need to do it very rapidly. So that's the important thing. So this is like cumulative CO2 emission, and this is annual emission. So you see China is moving really, really fast. So there are some initiatives, like I mentioned, Europe and United States, that's really track this emission a bit down. And you see this hiccup over there, that was for Corona. So it's all over. This 2020, 2021, you see overall, every country or global CO2 emission a bit lower, but now started again like high. So this is the scenario. Like I mentioned, many countries, they are emitting like billion tons per year. Many countries, they are emitting million tons per year. So this is more or less activities all over the world. If you see Europe, yes, a lot. US and Canada, and then some in China and Korea, Japan, in that area, a few about Australia. Africa, more or less nothing. Different color mean different thing. Yellow, those are the planning phase. Nothing happened yet. If you see those kind of color, like here, this is Insala, one of African oil field. They injected CO2, but then stopped. So there are many issues why they stop. And then, if in terms of operational, you see only 2 in Norway, basically in whole Europe, if you see. Then this is Snowbit, this is Sleipner, maybe you know about that. And only few all over. But a bit more in US. They have started and then took this thing very seriously. So we'll see more. But one of the important thing I mentioned here, like this one, why we see lots of discussion about Norway. Like all over the world, they think Norway is doing really great for CO2 sequestration, but where we are now. This history in Norway started in 1996, but that was not the purpose for the climate prevention. It was mostly from oil industry. One of field is called Sleipner, contained a high amount of CO2. It was discovered in 1974, but production started in 1996. Long, kind of break from discovery to production. But this high amount of CO2 concentration, you can't just sell that one. So in this field, they captured CO2 that produced with a hydrocarbon and then separated and re-injected in shallow level. So this is the reservoir level where they produce. So you see the depth around 3 kilometers. And then this shallow Utsira reservoir, that's around 1 kilometer depth. So that was the starting, and then company operated that field, really save a lot of money to give a tax to the government. So that's the history to start CO2 capture and storage. So this is one of snapshot, for this formation. Like I mentioned, most of the time you see in those target formation, we don't have real rock sample, mostly seismic and well log data. So in seismic, you see this is the area, that's the Utsira, top and bottom. CO2 should be injected within there. That's the reservoir, and on top of it, we have seal, and the focus for this talk is seal. Like if you have good seal, like here, CO2 will be restricted within that area. So this is one example. After injection of CO2, like 9 years and 13 years. So you see nothing before injection. Then every year in this Sleipner, they inject 1 million ton of CO2. So think about Norway emit 42 million tons. So we need, if like this size, 42 CO2 sequestration. And now you heard only one, like Longship. Initial target to inject CO2 1.5 million ton. So you can imagine we need another 30 in few years if you'd like to make just Norway net zero. Yeah? So in whole CCS process, then we have, like I mentioned, capture, different technologies over there, then transport, obviously pipeline, ship, many different roads like lorry could be transported, and then storage and monitoring. Storage could be saline aquifer or depleted hydrocarbon reservoir. So in that perspective, Norway is sitting really on a good level, because we have this offshore Norway, enormous understanding just for oil and gas exploration and production. So we know where we can inject CO2, and we know how much we can inject. It's a huge volume potential over there. So in our case, like geoscientists, most of the people here in the audience will focus for the storage and monitoring. So storage, it could be like mentioned, saline aquifer or oil and gas depleted field. There are some initiative about CO2 EOR, but it will not be happening in Norway. But a small option as well, like coal beds and like basalt, but it's very, very small possibility. You can't think about large-scale CO2 that we need for net zero. So it's nothing. And every aspect, like I mentioned, those are the reservoir where we should store CO2. And then on top of it, we have different kind of seal. Like seal will really cover that reservoir, and they are in different depth. They have different lateral continuity. So you really need to understand in different perspective, from geology to geophysics to rock physics to whatever technique we like to focus. So one of important thing I just would like to mention, CO2 is a tricky thing. They change their phase. Like, water, you have gaseous, you have solid form like ice. CO2 also form their, different phases based on temperature and pressure. So this is one of schematic, like, around 1 kilometer depth subsurface, you have a CO2 can, amount you need to store like this, but if it is going shallower and shallower, same amount will expand just from supercritical to gaseous phase, they will expand. And also if you see go down and down, it's not that much big difference. So that means one of challenge we have, if you go deeper and deeper, you have more pressure. That's natural system, you can't go that deep. And also drilling deep well, it could cost a lot as well. So suitable zone could be like, 2.5 to 1 kilometer within that depth level. Yeah, then most important thing, when we inject CO2, we would like to keep everything within that reservoir. And then in terms of time, here a diagram from present to many hundreds year, and then different trapping mechanism. When we inject CO2, instantly trapping mechanism contributes significantly, like 78%, just for how the structure is, where you are injecting CO2. And then in terms of time, few other things will come, like residual trapping, solubility trapping, and mineral trapping. So I'll not explain that much. Video will explain, so just wait a bit. This is the video made by European Union or Zero Emission Platform. They are the authority to suggest EU for CCUS technology development. Then it's a short video, can summarize the whole process, like how this CCS really work. So I'll not talk then within the time. You can just listen 3.5 minute video.
For CCS to deliver on its promise of reducing CO2 emissions, they must be safely and permanently stored underground. By injecting CO2 underground, we are in effect returning carbon back to where it came from. We extract carbon as coal, gas and oil, which are burnt to produce energy. The resulting CO2 emissions from power plants and heavy industry can be captured before being pumped underground, closing the carbon loop. How do we store CO2 safely and permanently underground? By imitating trapping methods used by nature to store CO2, gas and oil for millions of years. And by using existing technology to transport and inject the CO2. Technology which has been used for decades by the oil industry. Storage starts by pumping liquid CO2 into a carefully chosen reservoir. There are two main types of CO2 storage reservoirs: deep saline aquifers, which contain undrinkable salt water, and depleted oil and gas fields, both of which have the same key geological features to safely store CO2. A suitable CO2 storage reservoir needs a layer of porous rock at the correct depth to hold the CO2, sufficient capacity, and an impermeable layer of cap rock to seal the porous layer underneath. Once the CO2 is trapped under the cap rock, 3 additional mechanisms, residual, dissolution, and mineral trapping, ensure that the safety of CO2 storage sites actually increases over time. How do these mechanisms work? Some of the CO2 injected into the smaller pores simply cannot move, even under pressure. This is residual trapping. A portion of the CO2 dissolves into the salt water. This is called dissolution trapping. The CO2-rich water is heavier than the surrounding liquids and migrates downwards, where it may react to form minerals such as those found in limestone. This is mineral trapping. To ensure that a CO2 storage site functions as it should, a rigorous monitoring process begins at the reservoir selection stage and continues for as long as required. The well, cap rock, and adjacent rock formations are monitored for changes in pressure and CO2 concentration levels. All of these systems ensure that response times are swift and decisive action can be taken when necessary. Monitoring continues even after a well is closed, and EU law requires that stored CO2 is kept safely and permanently underground.
Yeah, so that's the whole story quickly in 3 minutes. And then again, my focus is for this unit. Like a black one you see on top, that's the cap rock. So I'll cover mostly on that afterwards. Yeah, I think I covered most of fun parts. Now a bit science we should focus. So first one, I can change now pointer. Yeah, like this. Second topic, study area, database, and method that I would like to cover. Like I mentioned, this is our playground. Norway and then Norwegian continental shelf from North Sea, Norwegian Sea, and Barents Sea. How much CO2 activities is going on? So far, like I mentioned, only 2. Sleipner is somewhere around there, here, and then Snøhvit over there. But that is related to oil and gas production and tax issues, nothing related to like CO2. So first one will come here. That's Longship or Northern Light project. You see background like yellowish polygon. Those are the areas so far Norwegian government awarded for CO2 utilization. So only 7 licenses so far. Within these 7 licenses, 3 over there. You see, if I zoom that area, maybe you are familiar with this giant trawl field. So surrounding the trawl, we have these 3 licenses. license number 1, that's called Aurora. And here, CO2 will be injected. That's kind of expectation from next year. That's the Northern Light project. And then another one east of Aurora is called Smehaya. And this is recently given to this winter shell, one of oil company, Luna. But that will come later. So this is mostly in really, really early phase. But why? Everybody thought Norway is really doing a good thing related to CCS, because we mentioned we have very, very strong record for oil and gas exploration, and that technology could be easily transformed for CCS. And Norway has started already like this one around 25 years back. So lots of understanding over there too. Yeah, then if you see a bit future perspective, this Northern Lights or Longship project could be kind of really a big one, can accept CO2 from many European countries. So that is a kind of opening, but still this Northern Lights project in phase 2, they will target only inject 5 million tons CO2 per year. So still only 5 million. If you think a global perspective and make net zero, we need much more than that. So this is just example like first CO2 license and Northern Lights. This is the well, it's called EOS. So one of reservoir, or basically two. It's called Johansson and Cook formation. That's nice porous and permeable sandstone. CO2 will be injected, and then there's the cap rock, it's called Drake formation. That will hold CO2. So you see, this is the trawl. Trawl basically producing from here. From here to this one, that's much deep, like 500-meter sediments in between, because the oil industry do not want to mix CO2 with hydrocarbon. So initial target like there. So this is one of simulation. After 25 years of CO2 injection, 1.5 million tons per year, this is the extent, like how it will extend. I mentioned also this other license, like Smehaya, that's the license number 2. Initial target for these two prospects is called Alpha and Beta. Capacity for this is like 200 million tons. So it's a lot. And those are only we are talking for, if it is this one, then yellow, that's the sandstone, like reservoir. And blue, not blue, green, those are the cap rock. So in this case, Sognafjord, that's the reservoir. Drapni, that's the cap rock. And then license number 1, this is Cook and Johansson, like I mentioned. Those are the reservoir. Drake is the cap rock. So results I'll show mostly for Drake formation a bit later. Yeah, then obviously you may notice all those licenses, we have only few wells, 1 or 2. Even Luna, we don't have any well drill yet. So seismic is an important part to understand this seal or reservoir. So seismic, 2D seismic, 3D seismic, well logs like here and there, those are the key database right now to evaluate any CO2 sites. And then if we have core cuttings, could be nice to add. Yes, then let's jump to results. So this is one of example like Aurora or Northern Lights injection point. Based on the topography, when CO2 inject, it will move in that direction. And all those lines you see, those are the fault. So it's kind of compartment. If fault is sealing, then it will not move here and there. It will be within this compartment and move until there. But to reach in that level, it needs 100 years. It's a far distance. And then first results, like I already mentioned. So this is exactly over here. And then even after 25 years, only migration, not even that level. But in 100 years, it could reach. Because you see, it's a sloping aquifer, and then lots of fault over there. So if some faults are, are permeable, then it will allow to inject CO2 and move further up. Yeah, so again, this is the stratigraphy. First results. Like I mentioned, we have to deal a bit science as well. So 2 parameters we really use to characterize a seal is called Young modulus and Poisson's ratio. To calculate this thing, we need some measurements like VP, POF velocity, SF velocity, and density of that rock, and that could come from well log and seismic. So this is the data, plotted from 3 wells, these 3 red dots you see, where we have all those measured data, no any prediction. And then under the classification, model behind this proposed by some people, like how those, shell could be fracked when you apply a stress, and when we plot our data on top of it, it does not match. Just for you see all the strain from ductile to brittle material, it does not match, because this model basically based from US. So it demands like we need some local. So this is another parameter just to see which really controlling this ductile and brittle behavior. So it's basically shell, clay. When you have more clay, shelly material, that could be more ductile. They have more capacity to hold. Instead of if you have more silt and sand, that will be brittle. So you have possibility to frack when you really inject too much and create enormous pressure. Yeah, then that was our understanding. Instead of like background trend, we have to treat differently with 2 parameters called acoustic impedance and shear impedance ratio. And those are the parameters we can easily extract from seismic. So that's we proposed, and then it's getting popular. So next step, instead of these 3 points, then you have just understanding here and there. But to understand whole area, you see many other wells are there, but most of the wells we don't have a shear wave. That's the main input for this Young modulus and Poisson's ratio calculation. So standard method, when we predict shear wave, it could be given like straight line. But then we use machine learning, and you see good capture. So this pink color, those are the real data, and this light yellowish color, those are predicted VS by machine learning. So machine learning basically playing significant role and giving much better understanding compared to, this is the standard method we use in well industry. Well industry in a sense is fine because we know already competent seal where we have hydrocarbon. But in CO2 we don't know. So it's like saline aquifer, when you inject then you'll see the scenario. So we really need to predict ahead. So this is again like when we have a VS prediction calculated these 2 important parameters, and then using all those wells and analyze the data in terms of ductile to brittle. So this background model I mentioned is proposed by Perez and Marford in 2014. And then also this is another popular method, Gracier and Bray, they proposed. So you see, this is the method basically proposed by them, 2007, and this is 2014, did not match. So it's a diagonal kind of relation. Then our method we suggested is also different. So this is method based on data from trawl area. So that could be more useful compared to other thing we discussed. So far results I have shown only well locations, but it's not enough. When you inject CO2, you should think about 3D volume, like how big area you are covering. So that means injecting CO2 here to understand all those areas, all sorts of data we have, we need to integrate and then map. Here, like I mentioned, only purpose for CAPRA. So this is one of, like a cross section from here, like this one to there, for this, seal or cap rock for northern lights. You see, they are sitting in different depths. They are in different thickness as well. And you see some areas they are missing too. So to extend or make these northern lights like in future 5 million tons or 10 million tons per year, we need to do a lot surrounding there. So those are the screening process to give a lot of idea. So when we think about seal, most important thing we have to see like depth, which depth they are. So this is the map for the just top of this Northern Lights CCS project where CO2 stored, this cap rock. this is the depth from 4.5 kilometer to 1 kilometer. So you see, when lighter color, those are the shallowest depth, deeper color, those are deeper. So it's blue, those are deep. So this Johnson and Cook, you'll find here 4.5 kilometer depth. Compared to here, this is shallow, like 1 kilometer depth. So those are the thing. Another important thing is thickness. Is it thin layer or thick layer? That you need to understand. So this is the thickness for that cap rock, from 0 to 100 meter thick. So when we have thick, look at there, those are the thick area, but those are very deep. Will not be helpful, you know. If you inject CO2 here, you need to drill 4.5 kilometer well, and it's too much. So those are the compromise, like when you think about depth and thickness. Then also this area, like I mentioned, trawl area, this is kind of stepwise uplift we have. When you move from Viking graben towards land, it's like uplifted. So you need to know this cap rock, where it is right now and how much uplift they have. Like when they buried, maximum burial they have. You have diagenesis, you have all those compaction processes, geologic changing, cementation. So that could give very good idea. That's why we need to understand uplift. So those are the uplifted area, like 1.5 kilometer. Here you see some areas like this kind of color, no uplift. And then we also need temperature. Like this is present day temperature experiencing that rock. But they buried deeper, that's why they have much more higher temperature they expose. So they keep their memory, like what's going on when they were deeper. And then last thing like this one I mentioned, brittleness and ductile. So when you have less value, like here, then those are the ductile cap rock. When you have reddish, those are the brittle cap rock. And you see the consequences with hydrocarbon field. When you have those kind of ductile behavior, you see most of the field over there. This is shallow, could be nice, but those are the brittle cap rock. So you need a good balance. And then also like shelliness. So everything I have shown there from well log, but in 3D, we need also to integrate seismic. So this is well log and seismic integration. This one for V-shell and two cap rock, you know, like I mentioned, this is reservoir, lower and upper deck. You see different volumes of shell between them. And then also their stiffness is different too. So like I mentioned, we have to deal a bit with science too. So far that's the results. And then just I would like to conclude. So this stiffness or brittleness, ductility we mentioned is basically calculated from elastic property. And then it's very nice and easy, if you have relevant data, before you do too much, you have nice screening and suggestion, okay, those are the potential area you can select. And then we also notice we should not randomly use models suggested from different parts of the world. We should use a site-specific or even formation-specific model. One of good thing we notice, this cap rock on top of Northern Lights CO2 storage is behaving more or less ductile, and that's a good news for Longship or Northern Lights project. Yes, just acknowledge, I mentioned two projects. One is called Oasis, another one Sense. Both are heavily focused for CCS, ended just before summer. And then we have funding from Research Council, European Union, and then also industry like Total and Equinor, and then different research partner, and we also need data from different sources, and then different tools to analyze. Yeah, so far that's it. Thanks for your attention.
Takk skal du ha, Nasmol,
Hyggelig.
for et veldig flott foredrag som de fleste klarte å følge uten problemer. I guess that you want your questions in English?
Yeah.
Yeah. So the floor is open for questions to Nasmol about his talk. Anyone?
Maybe I didn't catch it, but how do All right, thank you. I might have missed it, but going from points where you have data in the wells to the wider area covered by seismics, do you use how do you get the shear modulus out of the seismic data again?
Yeah, now that's another big area to work on. That's the inversion of seismic data. You can invert seismic and then acquire properties like BS, BP density, and then utilizing equation, you can calculate Young modulus and Poisson's ratio. So there are methods. So you need some sort of a spatial data like pre-stack data, and then you need to do pre-stack inversion. And then inversion, there are many methods too.
Cool, thanks.
Hey, Nasmul. Oh, does it work?
Okay, hi.
Very nice talk, so thanks for that.
Thanks.
I was wondering if you could comment a little bit further on you are working on looking into data to look into brittle versus ductile behavior of these shales. But can you comment a little bit on? Can you comment a little bit on how the brittle ductile axis?
Yeah.
What that means for the shale to hold pressure, for example, capacity.
Yeah. So the most important thing, to make any rock ductile, then you need kind of low Young modulus and relatively high Poisson's ratio. And then most of the time you'll get that when you have clay materials and less cement. But when you add cement and more silt and sand, so all data will move like this upward direction. But those are also tested in the lab. Like, you need to test in lab, like when they frack, you have the caprock and reservoir scenario and then inject CO2, see how much capacity they can hold, because you know the pressure, and at one level you'll see they will frack. But when you have ductile behavior like lower there, they will not frack. They'll just bend and try to hold. So that's the advantage here.
As you showed in your model, the top of the structures and that's the areas also with the lowest thickness of the seal are frequently affected by larger faults. And the larger faults are mechanically inhomogeneous. And so your ductility factor will actually not be homogeneous within the fault. Do you include that parameter into your models?
Yeah, like in a stress strain scenario, absolutely important. Also, at least right now, is kind of target to inject CO2 away from the fault. Like this one, those are the big fault. So obviously injected CO2, and then when you select a location where you see the movement of CO2, based on topography, which direction they will move. So obviously, always better to see like they are behaving like what we want, but at one stage they may encounter a fault. And that's why I mentioned like that's another scenario, another direction, another understanding like de-risking fault. I did not consider here. Just for both of the sites I have shown, they tried to inject CO2 away from the fault. To reach the fault, it needs 100 years or even more.
I have two quick questions. The first is, what is the benefit of industry company to inject CO2? Since it's, I don't know if this can bring any money for them. The second question is, by injecting, for example, in a reservoir, it is way, for example, to increase the pressure in some reservoirs if they're extracting oil and gas?
Yeah, no, there are many different scenarios. Like I mentioned, reservoir could be in different depth. So which one is suitable? If shallow, obviously you need to drill less. That means saving money. But then you have to understand, like, some scenarios could really hamper over there. This is one of nice example. This one. Yeah, here. This alpha and beta structure. It was kind of planned to inject CO2 before these northern lights. But then it was noticeable, like just for this production of oil and gas from trawl, they are depleted. That means maybe you have connection. This fault somehow communicating these two blocks. So those are another scenario. And then this Sognamfjord formation over there is just like 800-meter depth. So when you reduce, if you have depleted scenario, it will just boom like, it needs enormous volume. That means for the time being, it is not suitable over there. You need to go further down. Yeah.
Okay, I think that was the last questions, even if there are people dying here to ask you questions. Thank you again, Nasmul, for a very, very interesting talk. And I wish you all back here for the next GeoWednesday next month. Okay.
Yeah.